Thank you very much for spending time with me. I am Yutong Zhao, a third-year PhD student at Stevens Institute of Technology, and my advisor is Dr. Xiao. Now, I'm going to talk about our work, automatically identifying performance issue reports with heuristic linguistic patterns. It is a collaborative work with Analytical Graphics Inc. Software performance measures how effective is a software system with respect to time constraints and allocation of resources. Bad performance can result in long-time execution, memory bloat, and even program crash. According to previous study, users are more likely to switch to competitors' products due to performance issues than due to other general bugs. Software practitioners use issue tracking system to record any issues reported to their system. The reporter could be customers who are using software and facing some issues, or developers who are testing and debugging. The tagging of performance issue reports in the issue tracking system relies on developers' experience and manual effort. But based on our observation, in practice, a large number of performance issues were not tagged and systematically managed. You may have heard of Apache software platform, one of the biggest open source software platforms. It hosted more than 300 open source projects, and we found that the majority of these projects have less than 0.1% of tagged performance issues. But empirical study has shown that performance issues should be around 4% to 16%. Currently, we have many advanced AI technologies, including natural language processing and many machine or deep learning models. They are very powerful techniques that hold great promise to help us automatically analyze text input and categorize them. But there are still some challenges. Some simple techniques like keyword matching are used in many previous studies to acquire real-life performance issue data, but it tends to miss excessive false negatives, and the keyword set is very limited. The machine and deep learning techniques also struggle because they are known to perform poorly in imbalanced datasets, and there are only 4% to 16% issues are performance related. We are facing a very imbalanced data. The gap is that the classic machine or deep learning methods failed to capture software performance specific knowledge as learning features. And here is where we made a breakthrough in our approach. So let's look at what is the secret sauce in our approach that will work very effectively. The secret sauce is the linguistic patterns embedded in the issue report. Linguistic patterns are grammatical rules that allow their users to speak properly in a common language. For example, this is a typical linguistic pattern. As a customer, I want to do something so that I can achieve certain benefit. It usually captures how a user story is described in Agile projects. And by matching these linguistic patterns, you can find the description of the user story. So, we stem from the observation of performance-related issues often contain similar linguistic patterns at the sentence level. And these patterns are agnostic of specific software product. That means we don't have to dive into technical details or domain specifics of a particular product. Here is the overview of our approach. It comes in two phases. First, the preparation and learning phase is to build a comprehensive set of linguistic patterns. In the second phase, we leverage the linguistic patterns that we derived from empirical study and manual observation and embed this knowledge into machine and deep learning techniques. The models can automatically decide if any given issue report is whether a performance issue or not. In the first phase, our goal is to extract a comprehensive heuristic linguistic pattern set from the known performance issue reports. As I have mentioned before, there are more than 300 projects on Apache platform, so we rank all the projects based on how many developer-tagged performance issues are available for us. Then we grab the projects with largest number of developer-tagged performance issues. Then we pre-process these issue reports using classic NLP package and start some manual tagging to annotate the most important information for us. Next, we start semi-manual extraction of heuristic linguistic patterns by using NLP knowledges. There are 4 different types of linguistic patterns, including the lexical pattern, which is similar to the basic keyword matching, the structural pattern, which operates on a higher grammatical level of sentence structure, the profiling pattern, which captures the performance characteristics of a system, and the semantic pattern, which extends lexical patterns by also incorporating sentimental analysis. After processing all the issue reports from one project, we will merge and consolidate the extracted patterns with whatever we achieved so far in the current iteration. In the update iteration, we will check whether the derivation has reached a saturation status, meaning are we able to find more new unknown patterns by looking into more projects. If we are just repeating the process but are not able to find new linguistic patterns, that means the linguistic pattern set is saturated. Once we have obtained the comprehensive linguistic pattern set, we are ready to do performance issue classification. Our approach works at 2 progressive levels, the sentence tagging and the issue tagging. The first level is sentence tagging. We break down each report into multiple sentences. For each sentence, we use the linguistic pattern set to match the sentence and calculate a vector. This vector describes how many patterns have matched by this sentence. And then this vector serves as the learning feature for a particular machine or deep learning model. The classic machine and deep learning model are like naive Bayes and decision tree, and the deep learning model include convolutional neural network, recurrent neural network, and BERT, etc. Finally, this machine or deep learning classifier will generate a tag at a sentence level. For the sentences from the same issue report, we further aggregate them as an issue level vector. The issue level vector is a sum of positive sentence vectors. It will serve as the learning feature of the issue classifier. Similarly, the issue classifier also uses the different machine or deep learning models. And finally, we can get the output of whether an issue report is performance related or not. Our work focused on 4 research questions. First, when can a heuristic linguistic pattern set become saturated? Meaning, there are more than 300 projects on Apache. Do we have to manually examine all projects? Or can we stop somewhere, like after 10 or 20 projects, until we see the pattern set to be saturated? The second question is, how accurate is our sentence tagging approach? In order to have an accurate issue tagging, we want to make sure the sentence tagging is accurate, and this would be measured by standard information retrieval metrics, including precision, recall, and FS score. Next, we can answer how accurate is our issue tagging approach. Finally, we want to see how much does the sentence tagging impact the accuracy of issue tagging. In other words, do we really need the two-phase approach? If we directly dive into the issue tagging, would we get the same good result? Our study contains 3 large-scale datasets of real-life performance issues. The first and the most important dataset is where the heuristic linguistic pattern set is built. It ends until we were able to rehash the situation status of the pattern set. We knew after processing 980 issues from 13 projects, the pattern set will be saturated. These issues contain more than 5,000 sentences, and around half of them are indeed talking about performance concerns. And based on this number, 980, we randomly select 2 more evaluation datasets. One is for homologous evaluation, which are from the same projects as the HLP set building dataset. In this dataset, you can see much lower percentage of performance issues and sentences, because the data is very imbalanced, right? The other is for heterologous evaluation, which are from the projects that are independent from the building dataset. To show the advantage of our approach, we compared our approach with a total of 31 baseline methods in 3 groups. They are machine learning models, deep learning models, and a simple keyword matching approach. Our approach also used these machine and deep learning models. The baseline methods were using classic natural language processing features. The first question is, when can the heuristic linguistic pattern set become saturated? As I have mentioned before, we start from the project that has the largest number of developer-tagged performance issues. In Apache platform, as you can see in this table, Impala has the largest number of developer-tagged issues. Then it's Oak. It turns out after 13 iterations, meaning after we reviewed 13 projects on Apache, we were no longer able to find more new linguistic patterns. As you can see on the chart here, it shows how the numbers of heuristic linguistic patterns change over iterations. The number increases quickly at the beginning of first few iterations. The precision remains pretty stable, and so it's a signal telling us we are doing a good job. The recall trend tells us the pattern set become more comprehensive. After 8 iterations, the recall remains stable too. RQ2 asks the accuracy of sentence level tagging. Our approach can provide up to 81% of precision and 79% of recall. And when we compare our approach with the baseline methods, we find that our approach can outperform up to 19 times of the baseline methods. And this figure here is just a comparison by using our approach with deep learning models in baseline 2. In our original paper, you will see the details of the comparison with many other baseline methods. The next question is the accuracy of our issue tagging approach. Our approach can provide up to 83% of precision and 59% of recall. You may be thinking the recall is not so high, right? But we think in our case, we actually value precision over recall. The reason is that if our approach provides much lower precision, the practitioners will be much less likely to adopt our tool because they will spend huge human effort for validating and excluding false positives if they have low precision. The good news is that when comparing to the baseline approach, our approach can still outperform them. As you can see on the chart, all the winners are combined with our linguistic pattern set. The first question asks how much does sentence tagging impact the accuracy of issue tagging. The purpose of this question is to investigate if we directly go for issue tagging without sentence tagging, will we still get the same good result? Here, the red line shows the precision and recall of direct issue tagging approach without using sentence tagging. And it turns out that if we add the sentence tagging, which are shown as a green line, the precision maintains very high, and the recall improves around 20%. Here is a summary of our contribution. First, we proposed a hybrid classification approach by combining classic machine and deep learning models with heuristic linguistic patterns. Next, we provide a comprehensive linguistic pattern set. Practitioners and researchers can use these patterns to build their new model to get their best results. The last contribution we made here is 3 large-scale datasets of real-life performance issues for related future studies. In the future work, we will build an off-the-shelf issue detector which can transfer issue reports to our interested information. Developers can use our detector to save manual effort for tagging issue reports. In the past, because of the lack of real-life performance issues, practitioners don't have a good understanding of what is the landscape of taxonomy of common performance issues. Once we have the detector, we would be able to accumulate a large-scale dataset of real-life performance issues. Based on that dataset, we can further categorize the types of performance issues and discover the common resolution of real-life performance issues. Also, our approach can extend to research of other types of issue reports, such as the security issues, etc. Okay, thank you for listening.